VITAS is a GMP-certified chemical analysis contract lab with 25 years' experience in providing high-quality, custom chromatographic analytical service based on cutting-edge knowledge and technology. VITAS originates from the Department of Nutrition, Institute of Basic Medical Sciences, University of Oslo, the largest department of nutrition in Europe. The CEO and Chief Scientific Officer is Dr. Thomas E. Gunderson is an experienced scientist with a significant list of publication within the field of nutrient and lipid biomarker analysis. Dr. Gunderson is also the principal scientist in several large-scale EU-funded research projects. The company is located in Oslo Innovation Center, the science park connected to University of Oslo, and the National Hospital, as well as several blooming Norwegian innovation clusters. The 750 square m R&D and GMP analytical lab facility is situated in Oslo Innovation Park's newest and most modern building, is equipped with an extensive and up-to-date inventory of scientific equipment. The laboratory is equipped with advanced HPLC, GC, UV spectrometry, fluorescent assays, ELISA, various mass spectrometric and other modern high-end techniques. For 25 years, VITAS has performed biomarker analysis for the Norwegian primary health care. By serving multiple Norwegian fish oil producers in lipid analysis in both R&D, optimization of production procedures, quality control and medicinal development, VITAS has gained cutting-edge knowledge on lipid chemistry and analysis. As one of the pioneers in modern use of dried blood spots, VITAS is recognized as a leading player within this field. The high-throughput DBS facility currently receives, analyses, and reports approximately 10,000 DBS sample every month. It is expected that this number will increase to 15,000/month within the end of 2017. Within the next 5 years, VITAS envisaged to perform more than 1 million DBS samples annually. VITAS contributes to an extensive array of scientific work every year, and over 25 years of operation, this has produced a significant list of peer-reviewed scientific papers. Thus, VITAS has accumulated an extensive and varied repertoire of skills and competence and a proven ability to produce high-quality experimental data that merits the publication in high-impact journals. Please visit the company webpage at www.vitas.no for further details. Thomas E. Gunderson. Oslo Innovation Center Gostadalene 21 N0349 Oslo, Norway. Phone, +47 229588631. Email, tag@vitas.no, tag@vitas.no org, hashtag 968655973. Oslo, May 20, 2020. Destruction of samples. VITAS AS is a privately owned GMP-certified contract laboratory. The company was established in 1994 as a spin-off from the Institute of Nutrition at the University of Oslo. The company delivers an advanced high-quality service to various industries, including universities and other academic institutions, primary health care, food industry, dietary supplement, and pharmaceutical industry. One of these customers are Zinzino AB. Zinzino's customers send blood samples as dried blood spots to VITAS in Oslo by regular mail or by express courier transport. Upon receipt, samples are registered and analyzed for the agreed biomarkers only. The sample is kept for 14 days post-analysis to be able to do confirmational analysis in case of customer complaint. The sample is then moved to special biohazard containers, sealed and collected by a contracted company that specializes in handling biological material and destroyed by high-temperature disintegration. This procedure is described in Vita's internal SOPs. Yours sincerely, Thomas E. Gunderson, PhD CEO. www.vitas.no Balance test. Self-test for analyzing fatty acids in the blood. Highlights regarding balance test. Zinzino's balance test is an easy self-test for analyzing the fatty acids found in capillary blood obtained from a fingertip using the dried blood spot, DBS, technique. A DBS is scientifically proven to be as accurate as a venous blood sample when fatty acids are to be analyzed. All it requires is a few drops of blood from the fingertip on a Wattman-registered filter paper, and it takes less than a minute to complete. Vita's analytical services in Norway will anonymously analyze the percentage content of 11 fatty acids, which together represent approximately 98% of the fatty acids in the blood, and the values reflect your diet for the last 120 days, which is the lifetime of blood cells. The result is then displayed, after about 10 to 20 days, on the zinzinotus.com website. Easy-to-use dried blood spot self-test. Measures 11 fatty acids in your blood. Provides data about your omega-6:3 balance. Key benefits. How does it work? You should take your first asterisk balance test, and then start at once to take your daily dosage of Zinzino balance products. Continue to take the balance products as recommended for 120 days, and then take your second balance test to find out how your fatty acid profile has changed. Asterisk should your initial results show an omega-6:3 balance of 3:1 or better, then you should contact Zinzino since you do not need the balance product. What we measure: the test measures 11 fatty acids, including saturated, monounsaturated, omega-9, and polyunsaturated, omega-6 and omega-3, fatty acids. Individual fatty acid values are shown in the table and expressed as percentages of the total fatty acids measured. For comparison in the table, the average range for each fatty acid, based on data obtained from a large group of balanced people, is presented as target value. The following fatty acids are measured. Palmitic acid, C16:0, saturated fat. Stearic acid, C18:0, saturated fat. Oleic acid, C18:1, omega-9. Linoleic acid, C18:2, omega-6. Alpha-linolenic acid, C18:3, omega-3. Gamma-linolenic acid, C18:3, omega-6. Dihomogamma-linolenic acid, C20:3, omega-6. Arachidonic acid, AA, C20:4, omega-6. Eicosapentaenoic acid, EPA, C20:5, omega-3. Docosapentaenoic acid, DPA, C22:5, omega-3. Docosahexaenoic acid, DHA, C22:6, omega-3. Independent laboratory or test is analyzed by an independent and GMP-certified laboratory. The fact that Vitas is GMP-certified means that they follow good manufacturing practices. They are a contract laboratory for chemical analysis with 25 years of experience, providing high-quality chromatographic analysis based on cutting-edge knowledge and technology. Included with the blood test is a balance test ID that only you can see. Neither the lab nor Zinzino knows who submitted the test. At zinzinotis.com your results will be displayed when you enter your balance test ID. If you have completed the questionnaire, you will have access to the complete analysis. If you have not completed the questionnaire, you will see your balance score only. Certified Test KIT. The Zinzino dried blood spot test is certified to comply with the European Regulation 98/79/EB on in vitro diagnostic, IVD, medical devices. This means the test and all its components are in compliance with applicable laws and regulations, and so the kit has the CE mark on it. This is how your results are calculated. 11 fatty acids are analyzed, and the total sum of their amounts is considered 100%. For the following 6 values, we use 7 of the fatty acids. The analyzed amount of each of the 7 fatty acids is calculated as a percentage out of the 100%. 1. Omega-3 eicosapentaenoic acid, EPA. 2. Omega-3 docosahexaenoic acid, DHA. 3. Omega-3 docosapentaenoic acid, DPA. 4. Omega-6 arachidonic acid, AA. 5. Omega-6 dihomogamma-linolenic acid, DGLA. 6. Saturated fat, palmitic acid, PA. 7. Saturated fat, stearic acid, SA. Protection value. First, the following 3 recognized health indicators are calculated. 1. The value for the omega-6 ratio is calculated like this. DGLA plus AA, asterisk 100 slash, DGLA plus AA plus EPA plus DPA plus DHA. 2. The value for the omega-3 level is the sum of EPA plus DHA. 3. The balance value is calculated as omega-6, AA, slash omega-3, EPA. Each indicator value is given the same weight in a second calculation, and assigned a value between 0 and 100, which is then divided by 3 to get the protection value that ideally should be above 90. This does not tell anything about the health status of the person, only the fatty acid protection level. Note: EPA and DHA values have a high impact on all the calculations, and if EPA and DHA percentages are low, then as a result very low, or even 0 protection values are not uncommon. Omega-3 index. The omega-3 index is the summary of the percentage values for the 2 marine omega-3 fatty acids EPA and DHA. The ideal combined level is at least 8%, but higher values like 10% are desirable. Omega-3s have many benefits because they are the primary building blocks in your cells. EPA is dominant in the blood, muscles and tissues, while DHA is dominant in the brain, sperm and eyes. Omega-6:3 balance. The balance is calculated by dividing the percent value of AA with the percent value of EPA, AA/EPA, which is then expressed as a balance value, for example 3:1. The omega-6:3 balance in the body should preferably be below 3:1. If this ratio is above 3:1, you will benefit from a change in your diet. A low balance of omega-6 and omega-3 is important for maintaining normal cell and tissue development, homeostasis, and help the body control inflammation. Cell membrane fluidity. Fluidity is calculated by dividing the percent value of the two saturated fats with the percent value of the two omega-3s. The fluidity value is thus defined as PA plus SA / EPA plus DHA, and the result is expressed as a fluidity index, for example 3:1. If the fluidity value is below 4:1, it shows that there is sufficient fluidity in cell membranes. The more saturated the fats are in a membrane, the more rigid is the membrane. Conversely, the more polyunsaturated the fats are in a membrane, the more fluid is the membrane. Cell membrane composition and structural architecture is critical for the health of the cells and hence the body. On the one hand, the membrane needs to be rigid enough to provide sound cellular structural architecture. On the other hand, the membrane needs to be fluid enough to allow nutrients in and waste products out. Taking the test. Test 1. Balance test is an approved in vitro diagnostics product for personal blood sample collection at home. First, wash your hands with soap and rinse well with warm water and dry them. Take out the sample card from the paper envelope. Save the envelope for later use. Tear off the save part on the sample card and take a picture of the test ID. You can only see your test result with your personal test ID. Place the card with the two circles facing up on the table. 2. Use alcohol wipe to clean the tip of your finger. Middle finger is recommended. Stimulate blood flow by making big circles with your arm or shaking the hand downwards for 20 seconds. Take out the single-use lancet. Remove the transparent safety cap, and the lancet is ready to use. 3. Place the lancet against the lower part of the fingertip facing the collection paper on the table. Push the top of the lancet against the finger until you hear a click. The lancet will automatically make a small prick in the finger. 4. Don't touch the filter paper circles with your hands. Squeeze the finger gently one time and add several, minimum 3, free dripping blood drops to each circle marked on the sample card. The blood should completely fill the inner part of the circles. 5. Leave the sample card in a horizontal position at room temperature for at least 10 minutes for the samples to dry well. 6. Insert the sample card back into the paper envelope. Then place the paper envelope into the metal bag and close it. Important, do not remove the desiccant bag from the metal bag. 7. Place the closed metal bag into the big envelope with the laboratory address on it. Note: you must put the correct amount of postage, stamps, on the envelope before you put in the mailbox. 8. To register your test ID online, visit www.zinzinotis.com. This is the website where you can see your test results later. It takes 10 to 20 days until your results are ready. Important: keep the save part of the card. You can only see your test results on the internet with your personal test ID. ID. Mental strength. This is B9H7D819. B9H7D819. Zinzino test ID /code /NR/no/cody/cods/codas/numer/CHID del test /ID de la pareba/caudal testului. Sparas /Vergela /Zoppies AC /Sauver /Besparin /Sparin /Passerdat /Sudopidi /Sovgard r /Salva /Garder /ASE Pastora. Save. www.zinzinotis.com. XXXXXXXX. B9H7D819. Okay, no. Minimum 3 drops of blood / circle minimum 3 drop par blood / circle minimum 3 drabber blood / circle einakin 3 passara verta / impera a minsta costi 3 dropar af bli / circle veamalt 3 tilka verd / ringiga vismas 3 pilenus ascens / aptly bent 3 laces craujo / abscritimus 10 minced 3 drupels blode / circle mindestens 3 blutstropfen / Kreis presenagenige. 3 Kropelkuri / crag 3 Gotchi di sang / Sergio un minimo de 3 goddess de sangre / circulo minimum 3 Picaturi de sange / circ 3 Guts de sango minimum / circle legalab 3 sepver / ko Valeri Group, LDT 2 Gelas and Iovilco STR LT 03150 Vilnius I, Lithuan AI B9H7D819. Okay. B9H7D819. 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 Zinzino test ID / code / NR / no / cookie / cod / could / cods / codas / numer / CHID del test / ID de la pareba / caudal testului. Sparas / Vergella / Zoppis AC / Sover / Besparan / Sparan / Passerdat / Sidopiti / Sovgard R / Salva / Garter / ASE Pastra Save www.zinzinonist.com XXXXXXXX B9H7D819. Okay no. B9H7D819. B9H7D819. Zinzino test ID / code / NR / no / cookie / cod / could / July 20, 2017 Vilnius. Director Sigita Danilevicine. UAB, Valeri Group / IM. K 301507397 PVM Mach. K LT 10041169116 telephone plus 370 676 96681 info at valeri.eu. Directive. Medical device, dried blood spot sample collection card. 98/79/EB on in vitro diagnostic medical devices. Valeri Group, Company Code 301507397, hereby declares under its sole responsibility that the products RDA card copyright dried blood spot sample collection cards necessary for blood samples collection and transportation to the laboratory according to technical regulation for the safety of in vitro diagnostic medical devices, instruments, approved by Order Number 679 of 29 December 2001 issued by the Minister of Health of the Republic of Lithuania, hereinafter, regulation, are classified as other IVD medical devices, and are made in conformity with the applicable essential requirements on a given product specified in Annex I and Directive 98/79/EC of the European Parliament and of the Council on in vitro diagnostic medical devices. Relating fatty acid composition in human fingertip blood to age, gender, nationality, and N3 supplementation in the Scandinavian population. Linda C., Saga 1, Christian Hovde Leland 1, Runebang Lystad 2, Arne Reimers 2, and Elling Olav Ruck 1. 1. Department of Chemistry, Biotechnology and Food Science, Norwegian University of Life Sciences, AS, Norway, and 2. St. Olav's Hospital, Trondheim University Hospital, Trondheim, Norway. Abstract. This study investigated data obtained from whole blood fatty acid, FA, composition of 3,476 Norwegian and Swedish individuals, which provided background information, including age, gender, nationality, and self-motivated N3 supplement consumption. The aim of this paper was to statistically relate this background information on the subjects to their whole blood FA profile, focusing mainly on the N3 polyunsaturated FA, PUFA. Results showed that age had significant effects on the content of eicosapentaenoic acid, EPA, and docosahexaenoic acid, DHA, in blood lipids for the Norwegian individuals, while N3 PUFA supplementation had a positive effect on EPA and DHA content in whole blood for the investigated population. Gender differences were also found for individual FA. A correlation also exists with previous studies on the FA profiling of blood lipids, further validating the test procedure. Keywords: diet, fatty acid composition, home test kit, whole blood. Introduction. In the human body, fatty acids, FA, are incorporated in blood lipids, depot fats, and structural lipids in membranes, Rise et al. 2008. Hence the distribution of FA can be measured in various blood fractions and tissues, Baleen and Campos 2006. Dietary intake, lifestyle, intestinal absorption, and metabolism are various factors that affect the FA profile of circulating lipids in humans, Rise et al. 2007, Panagiotokos et al. 2009. In the Scandinavian countries, citizens have access to a home test kit for voluntary testing of blood for lipid profiling. The test involves absorption of whole blood from the prick of a finger on a special paper. In addition, a requisition form seeking information regarding gender, age, nationality, and N3 polyunsaturated FA, PUFA, supplementation is provided. The blood samples are analyzed by gas chromatography of FA methyl esters, FAME, by an accredited laboratory in Norway, after arrival by postal delivery. In this study, a dataset was obtained with results from whole blood FA analysis and background information of 3,476 individuals in Norway and Sweden. The aim of this study was to statistically relate the background information on the subjects to their whole blood FA profile, focusing especially on the N3 PUFA. Materials and methods. Subjects. The blood test was employed by individuals who were interested in a screening of their blood FA composition through the use of a home test kit, developed by University of Milano, Italy, St. Olav's Hospital in Trondheim, Norway, and is distributed by Atoga AS, Norway, as Oil for Life test. Individuals acquired the test kit through therapists, health clinics, sports stores, a web shop, and other sales channels in the two Nordic. ISSN 0963 to 7486 print/ISSN 1465 to 3478 online Q 2012 Informa UK, Limited. DOI 10.3109/0963748.2012.681631. Correspondence: Linda C., Saga, Department of Chemistry, Biotechnology and Food Science, Norwegian University of Life Sciences, P.O. Box 5003, N1432 AS, Norway. Tel, 4764966154. Fax, 4764965901. Email, linda.saga@umb.no. International Journal of Food Sciences and ISSN 0963 to 7486 print/ISSN 14 1465 to 3478 Online Q 2012 Informa UK, Limited. doi 10.3109/0963748.6.2012.681631. Correspondence, Linda C., Saga, Department of Chemistry, Biotechnology and Food Science, Norwegian University of Life Sciences, P.O. Box 5003, N1432 AS, Norway. Tel, 4764966154. Fax, 4764965901. Email, linda.saga@umb.no. International Journal of Food Sciences and Nutrition, November 2012, 63, 790-795. Int J Food Sci Knitter downloaded from informahealthcare.com by University for Miljo and BioVitenskap on October 30th, 12 for personal use only. Countries, Norway and Sweden. The results presented in this study are from tests taken during the period January 2009 to July 2011. Test kit. The content of the home test kit was as follows: User Manual, Graco AS, Norway, Requisition Form, Graco AS, Norway, for providing necessary information, gender, age, nationality, use of N3 supplements and date, the individual test ID to access results online, Graco AS, Norway, an absorption paper for the blood spot samples, Graco AS, a disposable automatic lancing device, MedGemi AS, Norway, aluminium bag, Wattman, Denmark, for preservation and storage of the test paper and an enclosed envelope, Graco AS, Norway, addressed to St. Olavs Hospital, Trondheim University Hospital, Norway. Self-administered blood sampling. Drops of blood were obtained from a fingerdip by use of the automatic lancing device. Subsequently, the blood drops were absorbed on a special piece of paper and thereafter added into a sealed aluminium bag for preservation and storage. A filled-out requisition form was sent together with the aluminium bag containing the blood spot sample in an enclosed envelope addressed to St. Olavs Hospital, Trondheim University Hospital, Norway. The anonymous tests were gathered and processed by the accredited laboratory personnel at St. Olavs Hospital after arrival. The postal delivery may vary from 1 day to 1 week depending on the place of departure. The process from the blood sampling to dataset is illustrated in Figure 1. GCFA analysis. The blood spot samples were stored at 48C after arrival at the hospital laboratory and were then prepared and analyzed within a week. The transesterification and extraction procedure was based on the method published by Marangoni et al. 2004, with slight modifications. Briefly, the pieces of absorbent paper containing the blood samples were transferred to screw-capped glass vials and treated with 1 milliliter of 0.5 mHCl in MeOH. Samples were then stored at 708C in a dry bath for 1H to achieve transesterification of Fa to FAME. After cooling, 1 milliliter of H2O and 1 milliliter of saturated KCl were added, before Fa were extracted using 2 milliliters of hexane. The solvent was then evaporated by N2, and the samples were redissolved in 50 milliliters of hexane. Resultant FAME were analyzed on a gas chromatography mass spectrometry system, HP Agilent 6890 GC unit, HP Agilent 5973 MS detector, Agilent Technologies, Santa Clara, California, USA. The GC unit was equipped with a 15M capillary column, Sapelco Omega Wax 100, Sigma Aldrich, St. Louis, Missouri, USA. Samples were injected with a split ratio of 100:1, and the column was heated from 150 to 2608C with a rate of 408C/min followed by 15 minutes of isothermal conditions at 2608C. Pure reference compounds were used as standards and all chemical and gases were of analytical grade. Heptadecanoic acid and tricosanoic acid were used as internal standards. 11 Fa were reported semi-quantitatively and expressed as percentage of the total measured Fa content in whole blood. The measured Fa were palminic acid C16:0, stearic acid C18:0, oleic acid C18:1 and 9, linoleic acid, La, C18:2 and 6, G-linolenic acid C18:3 and 6, A-linolenic acid C18:3 and 3, dihomoG-linolenic acid C20:3 and 6, arachidonic acid, AA, C20:4 and 6, icosapentaenoic acid, EPA, C20:5 and 3, docosapentaenoic acid C22:5 and 3, and docosahexaenoic acid, DHA, C22:6 and 3. The absorbent paper was tested with regard to the stability of Fa in the blood spot samples by storage and analysis of blood spot samples from type 0 during a time interval of 3 months with an internal standard as reference. Only minor changes in stability of the 11 Fa were shown at the end of the storage period, indicating stability of more than 2 weeks as demonstrated by Marangoni et al., 2004. Statistical analysis. The statistical analysis was performed in RVER 2.14.1, a free software environment maintained by the R Development Core Team, http://www.r-project.org. Analysis of variance and simple and multiple regressions were performed directly on unprocessed. Figure 1. Schematic overview of the sample giving and analysis process of whole blood obtained through a home test kit. 1. Blood spot sample from a fingertip absorbed on paper. 2. Sample and a requisition form sent by post to laboratory. 3. Gas chromatographic analysis of blood samples. And 4. Statistical analysis of dataset. Relating fatty acid composition 791. Int J Food Sci-Nitter downloaded from informahealthcare.com by University for Miljo and BioVitensCap on October 30th, 12 for personal use only. Data to find differences between groups, e.g. nationality ties, and linear trends, e.g. age effects. Age groups equally spaced with 5-year intervals from 10 to 80 years of age were formed to give impressions of age-dependent differences, e.g. between males and females, and to indicate distributions of the subjects. Because of the limited number of subjects below 10 years and above 80 years of age, these were all taken out from the analysis. The responses were transformed using the natural logarithm to obtain normally distributed residuals and improve the explained variance. The Fa, EPA and DHA were selected as markers for N3-PUFA content in whole blood. Results. Characteristics of individuals. The investigated population included 3244 Norwegians, 1885 women and 1359 men, and 232 Swedes, 128 women and 104 men. The mean age of the Norwegian individuals was 46 years for women and 41 years for men. Of the Norwegian subjects, 56% declared a supplementation of N3-PUFA. The mean age of the Swedish individuals was 51 years for women and 46 years for men, with 45% of the Swedes declaring PUFA supplementation. Blood Fa composition, age and N3-PUFA supplementation. Figure 2 illustrates incidences of N3-PUFA supplementation within and between age clusters of the investigated Norwegian population. The most prevalent users of the home test kit and also of N3-PUFA supplements in Norway were in the age range of 45 to 54 years. The higher use of N3-PUFA supplementation seen in this group was not observed in the younger age groups, 20 to 34 years. A multiple linear regression relating N3 long-chain PUFA's EPA, 20:5 and 3, and DHA, 22:6 and 3, in whole blood of Norwegian individuals to age N3. Supplementation and their interactions were construct. The results are shown in the effect plot in Figure 3. As expected, Vizioli et al. 2003, Sands 2005, Barcelo Coblin et al. 2008, our findings show that proportions of EPA and DHA in blood were significantly higher among Norwegian individuals using N3-FA supplements, compared to individuals not consuming N3 supplements, Figure 3. The average whole blood EPA-DHA of the Norwegian individuals not consuming N3-PUFA supplements was 4.9%. SANS ETAL, 2005, reported the same average value for individuals not consuming N3-FA, when FA in red blood cells were analyzed. The multivariate analysis reveals that age has a significant effect on EPA-DHA content in whole blood of the investigated Norwegian population, also illustrated in Figure 3. Individuals in the age groups 10 and 70 years were not included in the multivariate analysis due to the small number of samples. A regular increase in EPA-DHA with rising age is seen for individuals who do not consume N3-PUFA supplements, Figure 3. The interaction between age and usage of N3-PUFA supplements also gave a significant effect on EPA-DHA content in whole blood. The data obtained from the Swedish population regarding EPA-DHA values showed higher variations compared with the dataset of the Norwegian individuals, Figure 4, also expected in a smaller control group. The effect of age was also significant for the Swedish individuals, as found for the Norwegians. N3-PUFA supplementation had a significant effect on EPA-DHA in blood lipids with a p-value of 0.03. No interaction effects were found. Concerning the proportions of FA in the Norwegian individuals, palminic acid, 16:0, oleic acid, 18:1N9, and La, 18:2N6, account for the highest percentage of total FA in both groups. Palmitic and oleic acids show higher proportions in the group not consuming N3-FA on a daily basis. By contrast, La shows the highest proportions in those consuming N3-FA. Supplements. AA 20:4N6 was the predominant. 1010 to 1415 to 1920 to 2425 to 2930 to 3434 to 3940 to 4445 to 4950 to 5455 to 5960 to 6465 to 6970 to 7475 to 7979 age. Number of individuals 200 150 100 50 0 0 N3 users others. Figure 2. Overview of numbers of Norwegian individuals consuming, black columns, or not consuming, gray columns, N3-FA supplements, according to age. 792L, C, Saga ETAL. Int J Food Sci Knitter downloaded from informahealthcare.com by University for Miljo and Biovitenskap on October 30th, 12 for personal use only. LC-PUFA in both groups, but individuals not consuming N3-FA supplementations had a higher proportion, 9.3%, in whole blood lipids. As a result, the total N6-PUFAs were significantly higher in the group not consuming N3-FA supplements. Proportions of FA found in the Swedish individuals were the same as for the Norwegian individuals, with palminic, oleic and La accounting for the highest FA percentage composition, Table I. Proportions of oleic acid were generally significantly higher among the Swedish compared to the Norwegian individuals, Tables I and II. Higher proportions of the N6-PUFA AA, as well as higher total N6-PUFAs were found in Swedish individuals not consuming N3. EPA and DPA and, hence, total N3-PUFAs were significantly higher in Swedish individuals consuming N3 supplements. Blood FA composition and gender. Table 2 gives the FA composition of blood samples from individuals in the Norwegian and Swedish population, subdivided into men and women. 57% of the Norwegian and 48% of the Swedish women declared a daily intake of N3-FA supplements, while 51% of the Norwegian and 40% of the Swedish men declared the same. The main difference in FA profile between men and women among the Norwegian individuals in this study concerns the significantly higher monounsaturated oleic acid in men. Higher levels of the N6-FA, La. 8.0, 7.5, 7.0, 6.5, 6.0, 5.5, 8.012, 7.5, 7.0, 6.5, 6.0, 5.5, 10, 20, 30, 40 age. EPA plus DHA, percent. 50, 60, 70 N3FA supplementation, yes, no. Figure 4. Effect plots presenting the Swedish individuals. 1. Effective age on EPA and DHA levels in whole blood. 2. Effective N3FA supplementation on EPA and DHA levels in whole blood. Effects of age and N3FA supplementation gave p-values 0.05. N3FA supplementation, yes. 8, 7, 6, 5, 8, 7, 6, 5, 10, 20, 30, 40 age. EPA plus DHA, percent. Age 50, 60, 70, 10, 20, 30, 40, 50, 60, 70. N3FA supplementation, no. Figure 3. Effect plot presenting EPA and DHA content in the blood of Norwegian individuals at different ages consuming and not consuming N3FA supplements. Effects of age, N3FA supplementation, and the interaction effect gave p-values 0.01. Relating fatty acid composition 793. Int J Food Sci Knitter downloaded from informahealthcare.com by University for Miljo and Biovitanskap on October 30th, 12 for personal use only. And AA were observed in women. On the other hand, women also had significantly higher proportions of the LCPUFAs, EPA and DHA in whole blood lipids compared to men. It is also of interest that the levels of DPA are higher in men than in women. GLA, ALA, and DHGLA are substantially the same in the two genders. Total N6 and N3 PUFAs were both significantly higher in women. Profiles of individual FA in the Swedish men and women mainly show the same trend as for the Norwegian men and women. Except for the significant difference in LA and total N6 proportions between Swedish men and women, no significant differences could be detected. Discussion. This study describes the blood FA composition of Norwegian and Swedish individuals who have used a simplified analytical approach for voluntary testing of blood lipids. The use of a home test kit for obtaining a blood spot sample is an easy-to-use option, which is applicable to all population groups. Marangoni et al. 2004. Mean values of the FA composition of the Norwegian individuals are not to be viewed as cross-sections of the Norwegian population, but the connection between blood lipids and the background information of the population should be representative regarding relative changes, considering the high number of samples. The cost of the test, which is to be paid for by the purchaser, and the individual's personal interest in acquiring such a test are limiting factors that do not make the home test accessible to everyone. Important background information for interpretation of the data, such as the description of the sample. Giver's dietary habits is not reported. In this respect, suppositions of the background for the FA results are difficult to assume. Several studies have indicated positive correlations between dietary intake and FA composition in diverse blood fractions when dietary habits have been investigated. Garland et al. 1998, Hibble et al. 2003, Kariki et al. 2003. Correlations between age and the content of N3 PUFA in blood lipids were observed for Norwegian individuals in this study. Similar observations were seen in plasma concentrations of Japanese women, and were also related to dietary intakes. Kariki et al. 2002. Table 2. FA composition of whole blood lipids in Norwegian and Swedish individuals, men and women. Norwegian Swedish. Fatty acids men women. SFA 16:0, a 22.6 carat 3.0 22.0 carat 3.0 22.4 carat 2.3 21.9 carat 3.1 18:0, a 12.8 carat 2.0 12.7 carat 1.8 12.8 carat 1.7 12.5 carat 1.8 mufa 18:1 and 9 a 24.9 carat 4.5 23.7 carat 3.9 26.8 carat 3.7 25.7 carat 3.7 pufa 18:2 and 6 LA UB 21.7 carat 3.4 23.2 carat 3.3 20.6 carat 2.9 21.7 carat 3.3 18:3 and 6 GLA 0.6 carat 0.4 0.5 carat 0.4 0.5 carat 0.0
Our nature is a powerful designer. When nutrients are in the right balance, we get a superfood. Zinzino provide cutting-edge, best-in-class products from the new science of pharmaconutrition, which uses active nutrients from food to fight the imbalances in our modern lifestyle. Eating fish is healthy. It is a well-known truth that higher levels of omega-3 support a healthy heart, an optimal brain function, and your immune system. How much do you need?
To know this, you have to measure the balance of omega-6 and omega-3, which you can do with the Zinzino test. We have tested several 100,000 people. Our statistics show that 95 out of 100 have too much omega-6 and too little omega-3.
Our DNA was programmed with a 1-to-1 balance. Today, the average is 15-to-1. According to the World Health Organization, a healthy balance for the heart should be less than 5-to-1, while science recommends 3-to-1. Balance oil is many times more effective than normal omega-3 supplements. These ingredients help support in most foods that are rich in omega-3, like seafood, seeds and nuts. We find them also to be rich in polyphenols. Polyphenols are micronutrients known for their power to reduce oxidation in your cells and cell membranes. Sadly, the omega-3 industry ignored this important truth. They left out the polyphenols. Zinzino respects and understands nature. We combine the highest quality omega-3 with the most potent source of polyphenols from a pre-harvested olive oil. When this works together, it creates a powerful synergy. For the final touch, we added the sunshine vitamin, the key for good immune health. Vitamin D3. Add life to your years. There is no other product like Balance Oil. Test yourself and choose one of our Balance products. Balance Oil with great flavors, or Aqua X that mixes with water into a lemon drink.